So this week, or well, this section, these three sections, they're all going to be about undoing the derivative. And really, I want you to take a second to think about what the derivative tells us, right? It just tells us something about slope, nothing about the position of our function, right? So I make this point because it's going to show up here in a couple seconds. Well, I guess it's going to show up in these first couple slides. So we know what the derivative is. Like I said, it's just the slope of a function at a point, right? If we were to think of it in its like most basic form. So let's say we were given these two functions. We find the derivatives, right? It wouldn't be hard. So we find their derivatives. Now let's say we're given two other functions. We find their derivatives. Now we compare the derivatives of both sets of functions. Notice two functions have the same derivative here. And these two functions have the same derivative here. So if we're going to undo the derivative, what does that mean looking ahead? Let's say I just gave you I told you that there was a function with a derivative of 3. And I asked you to find the function. How would you do that? Well, looking up here at the slides, there's two different functions that give you the same derivative. So what do y'all think? I want to undo this derivative. It's not obvious right away, right? So the question, we want to take what's called an antiderivative of either of these functions. We're going to undo it. To undo the derivative, we're going to have to apply what's called an integral. We're going to integrate a function with respect to x to get the original function back.
That looks like one of those music symbols.
So what?
The little music.
It does. It does look like those. And I think it actually comes from it, but I don't know for a fact. Oh no, I know where it comes from, but that's neither here nor there. So what we got is this idea that we're given a function, capital F of x. And its derivative is going to be lowercase f of x. If this is the case, then the integral of lowercase f of x with respect to x is going to be equal to capital F of x plus c. Why is that? What's happening here? What do y'all think is happening here? Holy hell, there's a lot of slides. I forgot I made that many. Okay, so I'm going to jump straight to this example here. We've got this function here, and we're going to take the antiderivative of it, which means we're going to undo the derivative. When we do, we're going to get x cubed minus x plus c. Now really quickly, just checking this, take the derivative of all of this. You get this, right? So what this c is doing is it's making room for all possible solutions with that same derivative. All of these have the same slopes. They're just at different heights. These are families of functions whose derivatives are the same. And what the indefinite integral does is it solves for that family. And it says we don't know which particular one it is, but we know it's one of these. So tack on this c at the end to make room for all of these different possible choices. Make sense? So having said that, going all the way back,
You go back to slide 1.
not quite to slide 1.
Okay. Because you.
Yeah. So what we're going to do, what we're going to be saying here is that you're going to undo a derivative, get back to the original function, you're going to need to tack on the c because you don't know which one of those original functions gave you that particular derivative. That's it. So when you do these derivatives, you have to, I will fill ever, I will mark every question wrong, have to include the c. You have to include it. It's got to be there. I'm emphatic about it for a reason. It has a meaning, okay? This is a really common mistake, and that's why I'm being so emphatic about it. I will regularly forget to tack on that C even. Something easy to forget. That's why I'm making this point. Now, having said all of this, just some anatomy and definitions that are going on here. This funny S thing, it's called the integral sign. This whole thing is called the indefinite integral. We've got our differential here, which tells us what we're integrating with respect to. We've got what's called an integrand. That's the inside, what you're actually integrating. And then the integral sign just tells you, do the integral. So think of this kind of like a function. It's really an operator. And what it's saying is, you're going to integrate your function with respect to x. Make sense? Now, the reason why this is important, this dx, is we could imagine we have something like this tells you think of t as a constant and x as your variable. So integrate with respect to this thing, not with respect to t. Make sense what I mean? It also tells you something about how these derivatives are going to behave inside the integral, but we'll get to that in the next section when we start talking about u substitution. So, we say that the integral of our function f of x with respect to x is equal to capital F of x plus c if and only if the derivative of f of x, capital F of x, is equal to lowercase f of x. So this gives us a way of checking our work too. Integrate, get an answer. If you're not sure about your answer, take the derivative, see if it matches your integrand. Cool. So, really quickly checking out these 3 different examples. Let's work backwards. 2x, take the derivative of this. You're going to get 2 here, plus the derivative of a constant is 0. And what do you know? 2. X cubed plus c, take the derivative of this. Constant differentiates out to be 0. This becomes 3x squared. And what do you know? What your integrand is. So forth and so on. Makes sense? Now, like I said, we can do this forward and backwards, which means these two operations are inverse operations of each other. They're undoing each other in some sense. If I take the derivative of a function and then pass it through the integral, I'm going to get that function back out up to a constant, right? And if I integrate something and then take the derivative, I'm going to get that something back. Yeah. So just like with derivatives, we have rules. We're going to have basic rules of integration as well. The integral of a constant with respect to x is going to be that constant times x plus c. And that makes sense, right? Like, apply the derivative to the opposite side, you get back k. K times a function, if you were to integrate that, that is k times the integral of your function. Your sum and difference rules are just like with the derivative, right? And then we have the simple power rule. Now, we need to be careful with the simple power rule. Simple power rule doesn't apply when the power is equal to -1. Why is that?
Is it -1 not a real number? It'd be a negative.
You're on the right track in thought. Like, it's not that it's not a real number, it's that, let's take the derivative of x squared as an example. The first derivative is 2x, right? Now the second derivative is just 2. The third derivative is 0. The fourth derivative is 0. The fifth derivative is 0, 0, 0 forever from this point on, right? Is there anything we can take the derivative of to get x to the negative first power? There's one thing. There's only one thing. Hey, that's it. The one and only thing. So the reason why the simple power rule says n can't be -1 here is because the only thing that will give you x to the negative first power is the element. Make sense? Everybody cool with this? Like I said, you have the right idea of that. It's that there's just nothing that we can raise a power to, take the derivative of, and get x to the negative first power. That said, we could have x to the negative 1/2. We could have x to the 1/2. We could have 1/3. We could have whatever we want, as long as n's not equal to -1. Cool? So as a couple of quick examples, we've got some constants here. Let's look at C. So here we're integrating with respect to t. So that means what we're going to get out is a function of t, right? And that first rule told us this thing should come out to be -5 times t plus a constant. B should be x plus c, and A should be 1/2 x plus c. Same exact solutions, right? So, what about this? What about the integral of 3x? Well, we know we can pull out this constant, right? That was the second rule. Well, now we've got the simple power rule here. We want to divide by 1 over n plus 1. N here is 1. We're going to have 2 times x raised to the n plus 1. It's going to be 2 plus c. So this whole thing is going to come out to be 3 over 2 x squared plus c. Using that constant multiple rule with the simple power rule, then we want to reduce it by simplifying everything that we can. So the general process here, write out your original integral, rewrite it in the most simple way you can. Integrate, and then simplify. Pretty much the same rules that we apply to the derivative, except now instead of saying derivative, we're saying integral. Right? Okay. So what about these? How are we going to do these? I would like for y'all to try A and B, or I mean to try B. I'll do A and another one up here. We all working on B. So for B, who got 2 over 3 times x to the 3 over 2 plus c? Anybody? No? Let's see. Let's check it out. B, you can rewrite the square root as the 1/2 power, right? So applying then the simple power rule, we're going to get x to the 3 over 2 divided by 3 over 2 plus c. That thing's going to come out to be 2 over 3 x cubed over 2. I'm going to say x to the 3 over 2 plus c. We're looking at A, 1 over x cubed can be rewritten as x to the negative third using the simple power rule. We're going to get negative 1 over 2x squared plus c. I forgot to add my plus c. And this is why I was making the point about add the plus c. Keep it there. It is really easy to forget. And finally, just this extra problem that I wanted to throw up here. This thing can be rewritten as x to the negative 1/2. We're working through it all. So it's really, like I said, just backwards derivatives. The easiest way to start working on these problems is to look at what's inside your integral and ask the question, what would have this derivative? So you can start to work backwards with your derivative rules. Because that's all your integration rules are going to be, right? They're just going to be the backwards derivative rules. So having said that, what's A here? Anybody? Folks at home, what do you think A is here? Well, I feel like I really yelled at that time.
A little bit.
A little bit. I had to say it with my chest.
Well, if they were asleep, they would nap.
That's the theory, right? I mean, it is 8:30, so I don't know that I can blame them. Folks at home, what do you think A is? And don't tell me a letter. I'm docking points for every second that question goes unanswered. It is 8:30 on a Friday morning. I'd be hungover too as an undergrad. Okay, so the way to do these problems, looking at A here, we've got the integral of x plus 2 dx. First thing to notice, you got the sum and difference rule right here, right? Okay. Simple power rule. Integration of a constant, right? Really quickly, notice that the integration of a constant is just a specific point in the simple power rule, right? This is the case where n is equal to 0. Make sense? So really all you need to remember here is the simple power rule, and you can totally forget the constant rule entirely. Get what I mean? So here, this thing is going to come out to be 1/2 x squared plus c. And this thing is going to come out to be 2x plus c. Well, we can drop these parentheses. start grouping things together. We have two constants here. Since I don't know what they are, why don't I just go ahead and combine them together and call them a new constant? They're constants, right? Like they're not going anywhere, they're not changing anytime soon. So why don't I go ahead and say C is going to be equal to C1 plus C2, and rewrite this whole thing as the 1/2 x squared plus 2x plus C. Makes sense? Now take the derivative of this. What do you get? Yeah, x plus 2. So you get back to where you started if you took the derivative. So that looks good. I'm going to erase this and just put it up here for right now. This thing was 1/2 x squared plus 2x plus c. Now we're going to play the same game with b. X to the 4th minus 5x squared plus x, all integrated with respect to x. This is going to be equal to the integral of 3x to the 4th dx minus 5, the integral of x squared dx plus the integral of x dx, right? I just combined all the rules together. And doing the same trick with that c as what I did up here, I'm going to do that down here now. We're going to get, this is equal to 3 over 5 x to the 5th minus 5 over 3 x cubed plus 1/2 x squared plus c. Nothing too crazy here. Checking the work. Solution for B is the same. They applied the same trick to A. Okay, what about this? If this didn't make you say, oh, hell no, you're not awake. What are we going to do here? We're going to break this up. Well, first, we're going to break it up according to how we can break up fractions. You're going to say, all right, cool, this thing is x plus 1 over the square root of x. Let's integrate this with respect to x. Well, I can break this up into two different fractions. X over the square root of x plus 1 over the square root of x dx. I can simplify this, and I can kind of simplify that, right? So all we're doing here is we're saying that A plus B over C is equal to A over C plus B over C, right? Just taking advantage of that rule to break up this. Yep. So now we can rewrite this first term. It's just the square root of x, right? Actually, let's write it like this. Now we can more easily simplify this, right? This thing is going to come out to be the integral x to the 1/2 dx plus x to the negative 1/2 dx. That's going to give us n plus 1, right? 1/2 plus 1 x to the 1/2 plus 1 plus, here our n is negative 1/2 plus 1 over 1 x to the negative 1/2 plus 1 all plus c, right? Simple power rule, that's all I applied here. Everybody see that?
You say it's simple as.
What I did here was apply that rule right there, right? I said, all right, we've got an n. In our first term, it's 1/2. 1/2 plus 1, right? 1/2 plus 1. In our second term, it was negative 1/2. Negative 1/2 plus 1. Negative 1/2 plus 1. Now we're going to simplify all of this. When we do, this is going to come out to be 2 over 3, x to the 3 over 2, plus 2 x to the 1/2 plus c. This is n plus 1, then this is going to be 1 over n plus 1, right? And these are in fact the reciprocals of each other, so we know that it works. Make sense what I mean? So let's check this really quick. Checking it, we stop right here. You can go ahead and simplify it and factor it further, but this is a business calc course, not an algebra course. And I want you to focus on the calculus, not the algebra. Really cool with this? Now, what if I gave you a particular solution? What if I told you, hey, here's the derivative of your function, and at a particular x value, your function is going to be equal to 9. I want you to find the exact solution of your particular function. Now what? How are we going to do that? How are we going to find the exact solution of our function? Let's think about what all this does. First, I'm telling you what the derivative of your function is. Then I'm telling you your function, when x is equal to 1, function is going to come out to be 9. I know if I integrate this, I'm gonna get my function plus c back, right? And all that c is really doing is acting like a placeholder. It's letting me choose which exact solution I want, right? So let's check this out really quick. Let's go ahead and integrate 3x plus 5 with respect to x. Well, this thing's going to come out to be 3 times the integral of x with respect to x plus the integral of 5 with respect to x. And all of this is going to come out to be 3 over 2 x squared plus 5x plus c. And I argue that this thing is equal to our function. Okay, so if that's the case, we got that our function now is equal to 3 over 2 x squared plus 5x plus a constant. Now, I'm going to keep the purple actually. Now, the second condition tells us that whenever x is equal to 1, our function comes out to be 9. So 3 over 2 times 1 squared plus 5 times 1 plus c has to be equal to 9. Yeah? When we evaluate this, we get 3 over 2 plus 5 plus c is equal to 9. Well, we can rewrite all of these in terms of fractions of 2. Let's leave c as it is. Well, let's rewrite 5 and 9. So this is going to become 13 over 2, right? So it must be that c is equal to 18 over 2 minus 13 over 2, or this is just going to be 5 over 2. So what did we just find? Not what c has to be, right? So these two conditions allow us to find our function and our c, right? So putting all of this together now, we found that our function is equal to 3 over 2 x squared plus 5x plus 5 over 2. We found the exact solution, the particular solution to this system. So this is like solving for a variable, but with calculus now. Instead of being given the slope of a function and some intercept value, now we're given the derivative of a function and some particular initial condition value, and solving for what that function is. Everybody cool with this? Really, this isn't that different from what we did in algebra. Before we were given slope and some intercept or some other point. Now we're just given the derivative, which is the function of the slope of the original function, right? And some point. The same idea, just with calculus now. So comparing really quick, integrating, solving for C. Same idea. It's really not any different than what we've done in the past, except now we're using calculus to get the job done. The point, the moral of the story here is that anytime you're given a function, a derivative, and tell what the original function is at a point, well, then you can solve for the exact solution of that function. Cool. So again, what exactly is C doing here? It's kind of making room in our function, in our solution, to put our function in the right spot. So the C is really just saying, there's a bunch of possible solutions to this integral. And we don't know which one is your particular case. So this is a placeholder until you can find out which one is your particular spot. Make sense? So in the 5 minutes we have left, let's consider this last example. What's the integral of this? X squared minus 2x plus c. Yeah? Let's see it on the board. So what we're told here is that the derivative is 2x minus 2, right? And that our function at 1 is equal to 2. So integrating 2x minus 2 dx is 2 integral of x with respect to dx minus the integral of 2 with respect to x. This is going to come out to be 2 times 1/2 x squared minus 2x plus c, right? I applied the sum and difference rule here. And then I applied the power rule, right? So this tells us that our function is going to be x squared minus 2x plus c. Now f evaluated at 1 is equal to 1 squared minus 2 times 1 plus c is equal to 2. So this thing's going to come out to be 1 minus 2 plus c is equal to 2, or negative 1 plus C is equal to 2. Or C is equal to 2 plus 1, C must be 3. Right? So putting all this together now, our particular solution is equal to x squared minus 2x plus 3. We can factor that out if we wanted to. Everybody see that? Makes sense? So what we've just done is we said, using this first condition, these are all of our possible solutions. These are all the different functions plus C, right? Then we said, using the second condition, we know this point has to be along that line. It has to be a part of our function, right? So we solved for this exact solution. So checking everything, comparing, start off by integrating, solving for C, and you get your particular solution. And with that, that is time. If y'all have any questions, I'll stick around. Like I said, we're going to get up to 5.3 for the exam. The exam will be next week.